didn't do last time.
That's good. Does it work?
By the way,
Yay.
we need a new picture.
I know we do.
All these kids have grandkids.
I know. I'm teaching their kids now.
Except for Chris.
Okay, guys, welcome. Thank you for coming out here. Trying to get you guys out of here before the big part of the storm hits. I want to say hello to the Marin/Sonoma dancing community for coming here and supporting Steve. We have a NBL basketball championship game tonight, so I was expecting the crowd to be a little light, but that's great. If I could remind everybody to please mute these. If you don't have it on mute. Students with the clipboards, just turn it over, take some notes. Make sure you put who the presenter is, Steve Smith, on there. And then the article that was next to it, you guys have to do a supplemental article. We have provided you one. Mr. Carpenter has been doing that for us. So grab an article. You don't have to use that article, but you certainly are welcome to. My name is Kurt Kruger. I kind of run this place, and welcome. This is our 6th STEM Cafe for the year, and Steve is filling in for us. I had a geoscientist who canceled on me, and Steve's always been very gracious of filling in. Just upcoming on March 12th, we have a former student, Samantha Silvers, coming back to us. She is a storyboard artist, so we're kind of putting the A in STEAM. And she's going to talk about her journeys doing storyboarding for major film production companies. And she's also made some short films herself. So that will be interesting to have Samantha back. And then April 9th is not really a speaker, but we are going to do a special showing of a film called We Are Guardians, which are indigenous people in the Amazon rainforest trying to protect the forest, and it's their story. So something a little different. My planetarium show, my next one on February 26th. Will be Worlds Beyond Earth, which basically is exploring interesting places in our solar system. That full dome show is actually a new show for us, so we'll be showing it for the first time. All right, just a reminder, we have these brochures out there on the donation box. And donations help us obviously provide programs, bring it to the public. I have a school here on Wednesdays. I do elementary schools here. I had Manzanita 5th graders here, like 40 of them, and we did a nice 3-hour planetarium observatory, walking our planet models and things like that, and that supports us too. So, all right. So format for tonight is just a regular format. So we'll introduce our speaker. He will talk. We will do a little Q&A. We will take a break after Q&A. I do have some refreshments, sugar cookies with frosting. You gotta have frosting. And I put it actually inside so we can go out this door. There's an overhang because it's raining. And it's over there. I got a little decaf coffee and some water if you need a snack after this. And then during that, Steve is here available for any questions. Okay? All right. Here we go. You ready?
Oh,
okay, you got the clicker?
I'm ready to go.
Okay, so I won't tell the backstory. Well, I guess I will. I pulled out I think this is Steve's 3rd or 4th time doing STEM Cafe for us over the years. And so I pulled out, I always do a little bio at the beginning, and so I pulled out one of his old bios, and I was going to use it, and then, so this is the new bio. Okay.
Yeah, it's the new bio.
The new bio.
This morning, so it's all the recent stuff.
This is Valentine's edition of Steve's bio. Steve has been the astronomy mentor at the SPARQ Observatory, right out here, if you haven't seen it. Since it opened in 2014, he enjoys working with students as they work through their individual projects toward completion. When he's not working with the kids, he enjoys long walks on the beach in the moonlight. Unless he's doing astronomy, in which case he'd prefer the moon not to rise at all. Tonight's a full moon, by the way.
I know, and it's raining.
And it's raining, I know.
And the observatory's open.
Astronomy has an asterism, a small group of stars, called the Big Dipper. Most people call the Big Dipper a constellation. It's really not. It's an asterism. Steve is an avid swing dancer, and out on the dance floor, he has been known to be a bit of a Big Dipper himself. Nice. That's good. Like most of us, he has had his heart broken, and as such, is reluctant to put himself out there again. Aww. But sometimes a situation comes along, and he just can't help himself. Nice. I miss boots. Our fearless astronomy mentor also plays the piano, which is challenging enough for him just by himself. It doesn't help when somebody else demands affection. Steve also enjoys knitting, cross-stitching, and in his spare time collects rubber band balls. Okay, I might have added that. I did that myself. All right, sorry. Steve's topic for tonight is the ISS, and even though he's never actually been there, he asks for your kind tolerance as he shares with you a lot of secondhand information. But even if you love his talk, please don't offer your heart to him. He prefers big piles of cash laid at his feet, which he can then donate to the SPARQ Foundation. Good, nice. It's with great pleasure that the SPARQ Center welcomes back my friend, Steve Smith.
Thanks for having me back, and thanks everyone for showing up tonight on a rainy night. Apparently there's no dancing going on. This is not the right floor. Okay, so I'm going to talk about the ISS, but the first thing I want to talk about is what I actually do here at SPARQ. So I'm the astronomy mentor, and there are kids that are interested in astronomy, and I get to do one-on-one projects with them. So this involves, they get to go to the observatory. We do an orientation with the observatory. The equipment is very complicated. They have to learn all the equipment, how it all works. They have to learn how all the software works, and then they get to take pictures and they do work with the pictures that they have. The two things that we do are photometry, which is the measurement of stars from light, especially stars that are varying over time. So they'll take a lot of pictures over many nights. Usually in one night we'll get like 200 or 300 pictures. And we'll put all through that through a software program, and the kids will actually measure the number of photons that are coming in from stars that have hit the camera. They do those measurements. We try and be as professional as we can. When their project's done, they can send those measurements off to essentially a professional clearinghouse so that other astronomers can use their data for research. So that's one of the things we do, but most of the kids just really want to make pretty pictures. So we have the observatory open all night. I should mention that the kids are not here all night. We actually have it set up so that they can run the observatory remotely from their home computer. So that's everything from opening to the observatory to running all the software. The observatory automatically closes up in the morning, or if it closes up early if it's bad weather, so we don't have to worry about getting rain in there. But most of the kids like to do astrophotography, which is a million times harder than photometry, because you have to take a lot more pictures with a lot of different color filters, and then it takes a lot of time to put everything together to get a nice picture. So we don't have any photometry projects. We have photometry projects going on, but we don't have any that are far enough for me to show you some things. We do have a couple of astrophotography projects. So Kaylee is here. Kaylee's over there. She's very quiet. We're about a little less than halfway through processing her bubble nebula. The nebula is just a cloud of gas, and so we've only done the grayscale, the black and white. We haven't worked on the color yet, but this is what she has so far. So it's a very odd object. It's a bubble of gas in space. We're going to do the color processing next, and then we put it all together and get a nice color image. So that's Kaylee's project. And then Yesenia, is Yesenia made it?
It's a very large bubble.
It's huge. Yeah, it's really big. Yesenia, I think, this is one of the amazing things to me about some of the kids here. Is the kids go to school full time, they have all these extracurricular activities, and they have their astronomy project, and a lot of them have jobs on top of that. Yesenia couldn't get off work tonight. Her project is almost done, and this is the Crab Nebula, which is the most famous supernova remnant. It's relatively close, a couple thousand light years away. And she's almost done. I think we have like maybe another hour to go on it. And that's a close-up. So this is a supernova that went off about 1,000 years ago, and very well photographed object. As a matter of fact, right behind me here is a Hubble Space Telescope picture of the same thing. But that's Hubble, and this is like right out here by the parking lot. So it's pretty good. Pretty good. Okay. The reason I'm here is to talk about the ISS. I had lots of topics I could have chosen, but someone suggested the ISS, so I went ahead and did this. And I hadn't actually done a presentation on the ISS for about 10 years or so I had to do a lot of work to kind of get all this together. But for those of you that don't know, the ISS stands for the International Space Station, and it's called that because a lot of countries have contributed, primarily the United States and Russia, and also Canada, JAXA, which is the Japanese Space Agency, and ESA, which is European Space Agency, and then a lot of other countries have also contributed equipment or design work or whatever to it. So it truly is international. As of today, there have been 279 people on the space station, not all at one time, just a little bit at a time. It's usually about 7. I think the most they've had is 13, from 22 countries. So it's a really great example of cooperation in the sciences between countries, between different peoples. Especially right now, we have a little issue with Russia with some things. But up on the space station, it's détente. Right? They work together, they do experiments together, etc. So it'd be nice if we could get the world down here to be more like the world up there. Okay, so I'm going to start with the most asked question about the ISS or being space in general. And I don't want to wait till the end because someone's going to ask it, so I'm just going to get right to it. How does this work in space? All right, so they do have space toilets. These are not Home Depot toilets. These are very expensive NASA designed toilets. And there's 2 parts to them. There's the solid waste part, and then there's also the liquid waste part, the urine. So one of the things that you'll see in almost all these pictures of things, is you'll see handles. Because they're in microgravity, meaning if they're not strapped down, they need to hold themselves down to do whatever business they have to do. So you actually kind of hold yourself onto the toilet, and then, without getting too detailed about it, there is a suction device that helps you out. Okay. And for both the male and the female astronauts, they have funnels that are essentially suction tubes, and that's how you get rid of your urine. And then this is the amazing thing, because they didn't used to be able to do this, but they invented a machine that's up on the space station now that converts urine to drinkable water. I know. I know. Scotch, it'd be great if it converted it to Scotch, but liquid water. But this is really important because one of the ideas of the space station is to start to see how humans can work for long periods of time in space. If they have to go to Mars, if we have to go away from the Earth and be out, kind of gone for a long time, you're not going to be able to get water all the time. So they have to get water from somewhere. Urine is mostly water, so they have invented a system to do that. This is called the water reclamation system. It's a pretty big thing, but it does the job. So the urine is actually just recycled back into water. And as far as the other stuff, it goes into a trash bag with all the other trash, and they deorbit it, meaning that they put it into the atmosphere and just burns it in the atmosphere. So hopefully they get the right angle. If you don't get the right angle, it can skip off the atmosphere and go off into space. So that wouldn't be good either. If some aliens find it, they'd be going, oh my God, not a good thing. All right, so that's out of the way. Now I can talk about stuff that actually matters. This is a diagram of the space station with there's kind of two main parts to it. There's the main section which has modules and laboratories and things like that. Then we have these solar array panels, and there's this long truss that goes back and forth. There are also docking ports all around the space station where different capsules can come up. So in this illustration, there's a Soyuz from Russia over here. There's an ATV, which is from the European Space Agency. The space shuttle used to go up and dock, and now we have the SpaceX capsule can go up and dock, and the last one was the Boeing Starliner, which could go up and dock. And so, again, we have all these different countries. We've got Russia, Canada, which is what the most famous thing that Canada has on here is what's called the Canadarm or Canadarm. And the shuttle had one, and the ISS has one. And it's a really interesting kind of grappling crane thing that they can move around on the outside of the station. Japan has this module down here, which we're going to talk about a little later. So a lot of laboratories, a lot of living space. You have to remember when you're on the space station, you're microgravity. Imagine that this room is a library, and there are shelves of books, just like a normal library would have. Well, now imagine that the ceiling is a shelf of books, and you can just reach up there and pull a book down. So it's useful space. All of it is useful space. It's very jam-packed with all sorts of things because you can actually have things in every dimension without stuff having to hit the floor. All right, this is a little animation I found of how they put it together. This did take no, okay. So this actually took, whoops, sorry about that. I had to just push the right button. Yeah, it's on now, but it's not actually running. Not actually playing. Okay, well maybe I can play it myself. I'll just go through this. So this, all these modules and everything, sorry about this, it's a little jumpy. Took about 10 years to put all together. So every time there was going to be an addition to the space station, either Russia or the U.S. sent up either the shuttle or a Russian rocket with the parts in it, and they assembled in space. It took about 10 years to do. Let's kind of get to the end here. And hopefully the other videos that I have will work better. Okay. So 10 years to build. First one, let's see what we have here. Okay, so when it gets done, it's about the size of a football field. So pretty big, about 100 yards, kind of in all directions. 100 yards square in all directions. And again, we have the truss going across here, and kind of going like from front to back are the main laboratories and modules, living quarters, things like that. If I was at a football game and I saw this overhead, I'd probably get pretty scared. That's actually not out in space. No football in space. All right, so they had to get the parts up there, and they have to keep the parts together up there in space. And the problem is, of course, you put something up, it's going to come back down until you get farther enough away from the Earth. So the person who figured out how to actually do this lived a long time ago. Isaac Newton. He was working on gravity, was trying to figure out how gravity worked. There's the apocryphal story of the apple falling on his head, and all, we don't know whether that's true. But he did work out the first formulations for how gravity worked. And one of the ways that he did that was what scientists call thought experiment. There's no way to actually design a physical experiment to test what he had in mind, so you do thought experiments. The other famous physicist who did this a lot was Einstein. Einstein did a lot of thought experiments and then worked out the physics and then the math. So Newton worked in the same way, and his experiment for gravity was he came up with this idea of what has become known as Newton's canon. Imagine that he was imagining, okay, I'm on the Earth. What if I had a really tall mountain that I could put a canyon on top of? There's obviously no mountain that tall, but this is what was in his head. He was thinking a tall mountain with a canyon on top, and because we have a mountain, we got to name it something, so we'll name it Mount SPARQ. So what he imagined was, what happens if you fire a cannonball from a really high point or at different speeds? What would happen in that case? So normally, if you were just to shoot a cannonball and nothing else is interfering with it, there's no gravity, there's no other force acting on it, the cannonball is just going to go straight. It's not going to, nothing's going to interfere with it. It's just going to go like this forever if there's no other force acting on it. But if you're near a mass that has gravity and you fire a cannonball, it's going to go towards that mass. You add more gunpowder, then the cannonball is going to go farther. And what he was imagining was, how much, if you could like put unlimited gunpowder in there and fire a cannonball, you might be able to fire it fast enough that even though it keeps falling to the earth, it never hits the earth. So at that point, it's just going around the earth. It's still falling, but it's going fast enough that it keeps missing the earth as it goes. It's kind of always going by and missing the earth. And then once it goes back to the starting point, it's still got the same energy, so it's just going to keep doing that. And he realized that this is what an orbit was. That you start out, you have a system where you have the orbiting object have a certain amount of energy so that it always stays above the surface of the mass that it's orbiting. So in order for the ISS to be built, and in order for humans to go into space, you have to have a really big cannon. So this is Zarya. This was the first module for the ISS, launched in 1998 by Russia. Zarya means, anyone know Russian? The Russian speaker. Okay, Zarya means dawn, and what they meant obviously was the dawn of this big international project. So here is the cannon that Russia used. This is a proton rocket. This did work earlier, right, Kurt?
Yes, it did.
Okay. We shall see. I hope so.
To the internet still?
It should be. But this isn't an internet.
Oh, it's not? Okay.
No. Well, in any case, rocket goes up. Rocket's got to go really fast. And obviously, when a rocket goes up, carrying something, most of the weight that the rocket has is actually fuel to get fast enough to be able to get out of Earth's orbit with it. So the next question is, well, how fast do you need to go? The space station actually isn't that far away in terms of above us. It's only about 200, 220 miles. So it's not all that far. It's closer to us than LA is. But it is up there, not south. So you can do the calculations to figure out how fast you need to go. And this is not anything that any of us here are used to this kind of speed. But in the space station, because the space station is always kind of under construction, they have a construction sign, and when you drive by a construction site, and they have a speed limit sign, and it says 35 miles an hour work. The space station has the same thing with the speed limit. So this is how fast they're actually going. You have to go 17,500 miles an hour to orbit the Earth. So that's why you need a really big cannon, because you've got to get enough speed so that your cannonball doesn't fall back to the Earth. The problem is, if you go 25,000 miles an hour, you leave Earth's orbit completely and you go out. So there's this kind of sweet spot that you have to be in. Now this would be different depending on what planet you're on, because planets have different masses, and so you need different speeds to be able to orbit them. So if they go slower than this, they're going to start to descend into the atmosphere, start to burn up in the atmosphere. If they go faster than this, they're going to be like that cannonball that goes in a straight line because nothing's affected. So this is how fast they go. Nice brisk 17,500 miles. How fast I drive on one very club. It's a dance hall. So to give you a sense of how fast this actually is, I thought, okay, I'll do some math. I'll figure out how far is Santa Rosa to San Francisco. If I got my nice little yellow Porsche here, which I don't have, and drove it, how far? About 50 miles? 45, 50 miles, something like that. It takes about an hour and 15 minutes. So what I want to do is from Santa Rosa, I actually want to take the space station to San Francisco because it's a little quicker. So I'll take the space station. It's a direct route. It takes about 1.5 seconds to get there. So I have a Prius. I can get there pretty fast, but I can't get there that fast. I don't think a Prius downhill can get there that fast. So it only takes 1.5 seconds to get that distance. So again, this is speed that we're not used to dealing with down here, but just to give you an idea of what they have to do up there in terms of that. All right, so this is the orbit that they're in. Kind of jump around a little bit. So that's the track of the space station as it goes through each orbit. And because of the speed they're going, there are some really odd things that happen to you as a human being on the space station. One orbit around the Earth only takes 90 minutes. It takes an hour and a half. Okay? So one of the future transportation ideas that's been floating around for a while is how practical would it be to have planes or jet rockets that can hold a lot of people go suborbital. In other words, be able to go 17,500 miles an hour. If we can design a system that can do that, you can go from any spot on the Earth to any other spot on the Earth in 45 minutes or less. If you could do that. So there are plans for that are a lot closer to being in the works than like a Star Trek transporter, where your molecules get all, disassembled and then reassembled. So 90 minutes. So think about our day is 24 hours. A day, if you define a day by the sun comes up and then 24 hours later the sun comes up again. If you're going around the Earth once every 90 minutes, then you are getting a sunrise and a sunset every 45 minutes. So the sun rises, 45 minutes later the sun sets. 45 minutes later the sun rises. 45 minutes later the sun sets. So they're used to that. So they actually have 16 sunrises and sunsets every day, where we get one. But there's a downside to this. You're in space, you're outside of the atmosphere, so you're not protected by the atmosphere, so you just have radiation from the sun, and you have very cold space, and you don't have anything in between. So the temperatures on the exterior of the space station range from plus 250 Fahrenheit to minus 250 degrees Fahrenheit. So when they design spacesuits, for example, for the astronauts to go outside, spacewalks, they have to do maintenance on the station all the time. They do spacewalks almost every month. They just finished another one. They have to maintain equipment that's out there. They have to check experiments that are out there. They have to maybe replace some cabling or radio antenna or whatever. And so you can imagine they may be out there for maybe 6-7 hours at a time. And the spacesuit has to be able to withstand a 500-degree change in temperature. So this is not just, let's just go to space and hang out and do stuff. Because if you just hung out in space and did stuff, you'd be dead really fast. You'd either be frozen or you'd be on fire. So everything that they do has to be very carefully engineered and designed and tested so that there isn't harm to the astronauts. So that's one of the consequences of being in orbit and going that fast. The main reason the ISS is up there is because of human beings. We need to test how human beings do in space, how they do. If we end up going to Mars, we have a long trip to Mars. If we go up further in the solar system, these are really long trips. This is not just up to orbit and back. So we want to have human beings staying up there for a long period of time, and we want to actually measure as best we can whatever the physiological changes that happen to human beings when they're in space. It was bad enough if you were an Apollo astronaut. For some of you that are my age or maybe a little bit older, you may remember some of the Apollo missions. One of the issues with the Apollo missions was bathrooms. So what they did was they designed special food and drink for the astronauts so they didn't have to go that much. Things like that they had to think about. Like 3 days to the moon and essentially like something not much bigger than your bathroom at home with 3 guys. Must have smelled great. Okay, so but for longer periods we have to figure out actually how to live in space, how to actually work, how to survive, how to breathe, how to eat, all these different things. The other thing with the ISS is there are experiments that can be done on the ISS that can't be done on Earth because you're outside of the atmosphere and you're in microgravity. So these are the 2 main things the reasons why the ISS is up there. So first of all, physical challenges. You're in microgravity. We have evolved to be kind of here on the Earth, and everything's pulling on us on the Earth, pulling us down to the center of the Earth. So all of our bodily functions, all of our physiology has been adapted to suit us for that environment, which is not the environment they have here. The next thing is radiation. Our atmosphere protects us from harmful radiation. There's no protection in space from harmful radiation. And then we have things like space debris. They're not just man-made things like, there was an astronaut working on the ISS and she lost her toolbox. And so there's a toolbox out there in orbit around the Earth. There's all sorts of interesting things in orbit out there. But also little fragments of asteroids, little bits of rock that can come in and cause damage. And if a rock is hitting you at 17,500 miles an hour, I think you're going to feel it for like a millisecond before you don't feel it. So these are all very important things. And then the psychological challenges. We're not just physically designed to be on the Earth, but we're emotionally, mentally adapted to being here, to being in this, what we consider to be a very secure place. There's isolation issues, and we also have loneliness. Now, obviously, they're not very lonely right now. There's enough people up there all the time, at least 7 all the time, that you have people to interact with. So it's not like you're up there by yourself. The first astronauts that went up, both from Russia and the United States, those were capsules that held 1 person, and then 2, and then 3, and then the space shuttle went from 3 to 7. And then with the space station being built, again, the most they've had is 13. It doesn't quite look like 13. Pretty close. So these are some of the problems. Microgravity, things that happen in microgravity. We're always fighting against the Earth's gravity, so we're always getting muscle, and our bones are always working against Earth's gravity. You're out in space, you don't have that. So you have to compensate by doing a lot of exercise. So they have a cycling machine. And again, you might notice that she is holding onto handles Otherwise, she's just going to cycle right off. Right? She's got to hold herself in place. They have a lot of resistance training equipment, and just by looking at these pictures, you can see how jam-packed full the ISS is with equipment and things. You've got to have food, you've got to have water, you've got to have oxygen, you've got to have sleeping stuff, you've got to have clothes, you've got to have all this stuff. So it's all very carefully planned out and very dense in there. And then finally, they do have a number of treadmills up there. And this is Sunita Williams. She's up there right now, by the way. And the first thing you might notice about her treadmill is, first of all, it's really short. The second one is that she is strapped down. She has to be strapped down. Otherwise, she's just going to come right off the treadmill. Now, she's a really interesting person. So in 2007, she was up on the ISS in 2007 also. At the same time, they were running the Boston Marathon. So she ran the Boston Marathon on a treadmill while they were running the Boston Marathon in Boston. So, and I think she did it in like 4 hours or something like that. So pretty good.
I would think at 17,500 miles an hour, it would be running on track.
Yeah, that's true. She won. I think she got yeah. Oh, so a marathon is 27 miles. So that would be like 1 second. That'd be like 1 second at the speed. Okay, so that's so there. You have to do a lot of exercise to keep your muscle mass and your bone density kind of going. But even with all the exercise they do, they still lose muscle mass and bone density, regardless. So it's a challenge. I showed this picture earlier. I brought it back because you may notice his face looks a little bloated. And that's because you have fluids in your body and they're used to, your heart's used to working in a certain way, and all the other fluids, your lymph nodes, et cetera, are used to working in Earth's gravity. You don't have that anymore, then the fluids are kind of going to mostly equalize. And so the fluid that would normally be going down to your torso and your legs is going to go up to your head and your face. So when astronauts first get up there, they have this very bloaty face look all the time. And eventually that kind of goes away and isn't so pronounced. The problem is we have something really important in our head that is full of liquid, and that's our eyes. So one of the problems that astronauts have if they're up there for a long time is they have problems with their vision. The eyeball shape changes. It becomes more spherical. Does this sound like fun? Okay. There may be some beings out there who are completely adaptable to living in space, but we're not. At least not yet. So this is a problem. I wanted to specifically talk about water, because most of what we're made of is water, and we've got to have lots of water on the space station to do different things. There's a thing called surface tension of liquids. And so you've got, on Earth, you've got a drop of water, and gravity is pulling the water down. But there's also coherence in the molecules of the water that are holding them together that's keeping the water drop from completely collapsing. If it completely collapsed, you'd have a very thin layer of water that's just one molecule deep. Right? So you've got surface tension that is holding the water up. It's fighting against gravity. In space, you have no gravity. So the question is, how does water work? And this is going to be another video, so I don't know. We'll see. This is kind of
okay, so here's a soaking wet washcloth. Get the microphone so you can hear me while I'm talking. And now let's start wringing it out. It's really wet.
Surface tension holds the water in place because gravity will move it.
It's coming in a tube of water. The water's all over my hands. In fact, it rings out of the cloth into my hands. And if I let go of the cloth carefully, the water sort of has it stick to my hand. Okay, so the experiment worked beautifully. And the answer to the question is the water squeezes out of the cloth, and then because of the surface tension of the water, it actually runs along the surface of the cloth and then up into my hand, almost like you had Jello on your hands or gel on your hand, and it'll just stay there.
So that's surface tension with no gravity. There's no other force acting on the water, so the only force in the water is actually the cohesion of the molecules. I thought that was pretty cool. He also has played guitar in space and written a lot of books. He's an interesting guy. Okay. If you want to be taller, go to space because you don't have gravity pulling you down. So astronauts, if they're up there for more than a month or two, they get taller by at least an inch or two, which is really cool if you're a guy and you want to be tall. Tall, go up there. The problem is when you come back to Earth, and that is actually not pleasant. Either of them is not pleasant. But coming back to Earth, you lose whatever height you gain. So that's not a good thing. Okay. So when you get back on Earth, there's two ways. Well, there's a couple ways you get back. One is on the Soyuz capsule. This is the actual interior of the Soyuz capsule as they're getting ready to depart. When you go up to the space station, if NASA calls you up and says like go to the space station, and you go. They've cut down on the time. It's only like a day or a day and a half now for you to get there. When you leave, it takes you a couple hours to get home. They just drop you. They just drop you to Earth, and you kind of deorbit, and hopefully don't burn up in the atmosphere, which has happened. So even though this looks really like tight and cozy, you're not in there for like many, many days. But this actually isn't all that much smaller than what the Apollo astronauts had on the way to the moon. Not much difference. SpaceX Dragon, on the other hand, a little more modern, a lot more leg room, but still the same principle. You get in this thing, you detach from the ISS, and you sink to Earth. When you get out, you are not only have you lost bone density and muscle mass. Okay, that's true. That has happened. Now you're back in an environment where you need your bone density and muscle mass to hold you up. And so we're used to this. They're not used to this. So when they actually have to be helped out of the space capsule because they're so weak. And they go down this little slide, and then for quite a while they sit in this chair while everyone attends to them, and they get all their medical vitals and all that kind of stuff. And this is actually not fun. Astronauts have said like they try and raise their arm and they can't do it because it's too hard. It's too hard to do. It takes maybe like a week or two to kind of get back used to gravity, but it's really, really hard. So, are you better off staying in space? No, you're not better off staying in space because you have radiation. Kurt, how much? About 5-10 minutes?
Yeah, that's fine. Yeah.
An hour?
Yeah.
6 hours?
No.
Okay. All right, so we have an atmosphere that protects us from harmful radiation. So radiation, think of just radiation as waves on the beach. And waves that are coming in really fast at a really high frequency are high energy waves, and then you get slower waves. So on the slow end are things like radio waves. They don't bother us. And then you get microwave and infrared. We do get bothered. Infrared does have a temperature. We can kind of get that. Microwaves we're all used to. None of this stuff hurts us, right? And then we have the visible spectrum. So this is kind of in the middle of energy wavelengths that we can actually see. Then we get out into ultraviolet, and this is all the bad stuff. Even ultraviolet, we can all detect ultraviolet. Just go to the beach on a sunny day and don't wear sunscreen, and your skin will let you know you have detected ultraviolet. Right? You get sunburn. X-rays. There's a reason why when you go to the dentist, everyone else wears lead except you. Right? And then gamma rays, which are even worse. So the shorter the wavelength, if you think about the wave on the beach, the faster those are coming in, the more destructive they can be to your body. And we are lucky that we have an atmosphere that actually blocks or diffuses or reflects these higher wavelengths back out into space or absorbs them somehow. But out in space, you don't have that. So radiation becomes an interesting problem to overcome. This is an image from the SPARQ Observatory. This is from last year. Once every 200 or 300, 400 images or so, we get a gamma ray particle coming through. And that is that guy right there. Looks like a little streak on the side. Everything else, the white dots are all stars. But we do get occasionally a high energy X-ray or gamma ray coming through. So what's interesting about these is, you can imagine you've got a camera and you're taking a picture. I'm taking a picture of all of you. And all that I'm getting is the light that's coming into the front of the camera. X-rays and gamma rays can come in through the back of the camera, or the top of the camera, or the side of the camera, or underneath the camera. They can come in from any direction, and they just go through right, whatever is there. They just go right through it. So every once in a while, we get one of these, and it probably didn't come through the telescope and in the camera the normal way. It probably came in some weird sort of angle to everything. At the rate that we get them, they're not harmful to humans, but they do tell you, as you know, not to get a whole lot of X-rays. You just get the X-rays you need, and then do more. In space, there's no atmosphere. So this is a picture from SPARQ. This is a picture from Hubble, a raw image from Hubble. And all the little dots that you see, they're just kind of single dots. That's actually just noise particles that are part of the camera. But all these little lines that you see, these are all gamma rays. And these will go right through the space station and right through the people in the space station. So this is not what we're designed, not where we're designed to be. So we're trying to figure out how to guard against it. So thank you, atmosphere, for protecting us from all that stuff. NASA had a pair of twins. The one on the left, Mark Kelly, is now the senator from Arizona. Arizona, yeah. They were both astronauts, and NASA decided to do a twin study. First of all, hats off to them. That's like the best thing ever. Okay, so Mark Kelly stayed on the ground, and his brother Scott stayed on the space station for a year. A whole year on the space station. And mostly he did pretty well. His telomeres lengthened. Telomeres are, you have strands of DNA, and at the ends of each strand of DNA, you have a protective coating just at the end of it. And those are called telomeres. So as you age, one of the problems with aging is those telomeres get shorter and they expose the ends of the DNA to damage. And that can cause cell damage for us as we get older. His actually lengthened. They don't know why. And they have since gone back to normal. They don't know why. He was there, I don't know how long it was before he does have some genetic damage that he has not recovered from. So what will happen with high energy radiation, gammas and X-rays, they will go through your body and they will cut up your DNA. And those can cause, so that causes cell disruption function, which can cause cancers and cause some radiation poisoning and some other things. His cognition, they seem to think, has been slightly worse in speed and accuracy and has kind of stayed there. He kind of recovered some of it, but not all of it. Now that may be due to some external factors we don't know that have nothing to do with him being in space. And then there's also proteins that we have that regulate water absorption, and his were elevated. And so the whole thing about gravity and how fluids work and all that, the proteins that actually kind of help absorb water were altered somewhat. Okay, so the last thing, the main thing for physical things is impacts from space debris. So they do get little dings and hits. There's that first one there's a little ding in a window. That's on one of the solar arrays. This is in the Canada arm. Something hit it. And this is what a high impact looks like. That's it doesn't have, it can be a grain of sand going at 17,500 miles an hour. And that's going to cause some damage. So space debris is a real problem. There's also the issue of what's called the Kessler effect. So if something blows up in space and there's all these parts going out all over the place, they're going to impact other things that are in space and destroy them. And those things will break apart and spread more debris out and hit other things until all you have around the Earth is just a field of parts and debris. So that's a real concern. It's called the Kessler effect. Because normally on Earth, if you would have something break, it would just fall to Earth and be broken, and it wouldn't hit anything else except what was between it and Earth. But in space, you don't have that. Everything goes out in all directions, and so it can be. It's a real concern for scientists to figure out how to make sure that doesn't happen. Space debris is especially concerning during spacewalks. You're out there a lot more exposed than you are on the space station. There have been some minor incidents where someone's space suit has gotten punctured from something. And of course, there's a procedure that you have to follow to go back in. And that is not instantaneous. It takes some time to go back in the space station. So it's a very, when you say hostile working environment, this is the hostile working environment. This is not a great place to work. All right, I'm not going to talk too much about the psychological challenges. As a matter of fact, I'm just going to leave it because I don't want to talk about loneliness right before Valentine's Day. Okay. What do they do for food? That's the SpaceX Dragon. They bring up food and oxygen and other supplies from Earth, but it's also really important for longer space missions that they start thinking about how to actually grow their own food. So they do grow food. And we have a little video of a comparison. Hopefully, there we go. Growing something on the ground versus in space, and they have found that actually plants grow quite well in space. They weren't sure about the fluid, about how the fluids were transferred from the roots up to the plant, et cetera, et cetera. But it seems to be pretty good, and they get to actually have fresh salad that they've grown themselves on the space station. So there's some salad. We got some rice that they're testing. The whole thing is salad, and they've even got red peppers. So they're actually growing all this stuff in space. Pretty cool. I do want to talk a little bit about the Kibo Japanese experimental model and the exposed facility. So that's this thing out here. So one of the cool things about being on the space station is they built a porch. They call it the porch. And you can put experiments out on the porch which are completely exposed to the environment of space and see what happens. The main things that they are, here's a close-up of it, and it is just covered with instruments and experiments and all sorts. My favorite is this jack-in-the-box thing. I don't know what that is, but it obviously goes back in there. I don't know what it's measuring. The things that they're measuring primarily are cosmic rays, gamma and X-rays, because we don't get those on Earth. So the only place to measure those is up in space. They monitor Earth's atmosphere, and one of the big things is materials testing. So if you're going to build spaceships or stuff that's going to be exposed to space, you want to kind of have some samples of the materials that you think are going to work, put them up into space and see how they fare over a period of time. So really important for future space flights to have that. They've just done some spacewalks. This is a selfie that one of the astronauts took working on an X-ray telescope. The X-ray telescope is reflected here. It's this guy here. They were getting some light leakage from some wavelengths other than X-ray, and so they had to fix that. So they were only getting X-rays. This was a really interesting one that they just did finish like a couple weeks ago. You've got the space station that you're in, and then you've got an airlock and a hatch that you go out of. And what they were doing is they were checking on the outside to see if any microbial life from inside the space station managed to get outside and then stick to the space station. So they're actually kind of looking to see if there's any life that they accidentally kind of put out there on the space station. Okay, end of the ISS, and also the end of my talk, just under the wire. It's so sad. It's just really sad. This is a Valentine's Day, very sad. Decommission is scheduled for 2031, and there's no way to really do this gracefully. So what they're going to do is they're going to deorbit it. They're going to take everything off that they need to, and hopefully the astronauts too. And then they're going to just deorbit it in the atmosphere and burn it up in the atmosphere. It's been up there a long time. First module 1998, so it's been doing a lot of work. Okay, is that it? Oh, not quite. So you can actually see it. If you Google NASA Spot the Station, and you can put in your location. There's the website, and it will give you a list of when you can see the space station overhead. It's either going to be after the sun sets for like an hour or two, or before the sun rises for like an hour or two, because what you see is you see sunlight reflected off the space station view. So the angle has to be right between the sun and where you are in the space station for it to reflect light. So when you see it, it's not like they left all the lights on the porch on or something like that. It's just sunlight reflected off. So this is what we have coming up, and these are all for early birds. If you want to get up this early, and I would also, if you're really interested in doing this, please check the weather first. Because if it's cloudy, you're not going to see it. Clouds are between us and the space station. They're not too far up. Okay, so we've got some good passes coming up. The ones that you look for are the ones that are really long, like 6, 7, 4 minutes is great, and the altitude. And just really quick on altitude. That's altitude 0. This is altitude 90. So 45. So they have one that's 48 degrees, right? It's like a 45-degree angle, a little bit higher than that. And it tells you the direction where to go. So have your compass and kind of know your angles. Okay, I think that's it. I think that's what I got. Thanks for coming, and I'm happy to take questions.
Yeah, any local questions?
Why are they decommissioning it? Because everything wears out, and eventually things are going to get too dangerous. They've got a leak in the Russian section that they haven't been able to figure out. Yeah, so they get leaks, and you can imagine that they get fittings that kind of dry out, wear out. Plus, there's all this radiation hitting everything, and some things fare better in radiation. China has one up there now that they just started not long ago. I think the plans for NASA are not to go. This is called low Earth orbit, so it's like 200, 220 miles up. What NASA wants to do, although we'll see what happens with NASA now, what NASA is planning to do is to build bases on the moon and essentially have the moon be the International Space Station. So that has other problems besides this. It has all these problems plus some more. Yes?
So presumably they've got to get a little boost every so often to keep it in orbit.
Yeah, good.
How often does that happen?
Yeah, so they don't have a rocket on it like a rocket that takes the parts up. What they have is they have like little thruster engines kind of around the space station. And the main reason they need to have those is they do need to keep it up in orbit. So if it does start to sink down, start to drag a little bit on the very, very upper atmosphere, they'll bring it back up. But the main reason they move the space station at all out of its orbit is if they think they're going to collide with something. And then they have to know where, NASA knows where all the big stuff is out there. And they have to kind of move the space station either lower or higher, or in one direction or the other to miss what they think they're going to hit. So I want you to imagine that we're in the space station right now, going at that speed, and there's all this stuff out there that could just hit us at any minute. Well, it's kind of like being in earthquake country, I guess, or fire country. Okay, thank you. So they do have to maneuver with that.
Barbara?
Yeah, so they can't entirely protect them from radiation, all radiation, right? So in a long-term situation, really long-term, like living on the surface of the moon or Mars, would they have to live underground? Or would that make
what they're primarily looking at is they're trying to design materials that will deflect the radiation, the harmful radiation. That would be the best thing. But yes, they could go underground, but you still have to get there. So Mars is going to be several months to get there. Plus, you would have to ahead of time. If you wanted to do that ahead of time, you'd have to ship mining equipment there, to start to excavate to be able to go down. And some of that can be done automatically, without humans there. But my favorite fact about Mars is it's the only place that we know of in the entire universe that's entirely inhabited by robots that we put there. We put robots there. As far as we know, there's nothing else. So yeah, they think about going underground, but they're trying to find solutions for all possible solutions. And they may find a shield against radiation. Right now, if there's like a solar storm or something, and they think it's going to hit the space station, they will move all the astronauts to the far side to get as much of the space station between them and whatever's hitting them, so that it gets the harmful radiation gets absorbed by equipment and other things. But it's not like being on a boat where all of a sudden you go, right? Everyone's on one side of the boat. Yeah.
Last question.
Is the CO2 converted back to oxygen?
I don't know.
Fresh oxygen.
I don't know. That's a good question. Is the CO2 they breathe converted back into oxygen? I don't know. I don't know the answer to that. You may remember that Apollo 13 had a problem. For those of you that know the Apollo 14 story, they had a problem once they figured out how to get back home, that they were slowly poisoning themselves because they had no way to get rid of the CO2, and they had to kind of do a jerry-rig thing where they took things like part of a flight guide and duct tape, and there was a sock that they used, and they designed and built this thing that scrubbed the CO2 out, which was pretty amazing. But I don't know. I don't know the answer to that.
Thanks, Steve. Thank you all. Okay, guys. Yep. Steve will be here if anybody has any individual questions. If you go out that door and head into the other room, you'll see the other door open. There are cookies, coffee, water. Thank you for being here tonight. Students, please make sure I get my pencils and my clipboards back. It is raining pretty good outside. Please drive home safe. Thanks for coming.
So students, make sure you do your stuff. Answers work on your footwork. Right? Footwork.
Started.
I'm sorry, I always stand. Yeah, it's not a cool place. It's a worse problem.
There's some schools that have some observatories that are remote.
It's been 12 or 13 years from that astronomy. I was on the No, the moon is upside down. Hawaii is upside down. And water swirls. Thank you very much.
Oh, yeah.
Now that he's finally figured it out.
Now they know how he gets for
Although I'm not, okay, I was gonna say, I'm not so sure he does.
That's, yeah, that's kind of big he actually sponsored like go, yeah. He had another German Shepherd too called Big. So yeah, it's a big lug. It's a lovable dog. Yeah, it's a big, yeah.
Archie's that's when he puts his head on my lap. I mean, oh my God, my lap.
Yeah.
His head.
It's a big German Shepherd. But very gentle, very sweet dog.
Almost my husband's talking, right?
Big, big, big.
It's a big German Shepherd. It's bigger than most German Shepherds. Yeah. Which is a thing. If you leave appreciation something, you think it's bad.
Yeah. Yeah, that's
Yeah, no, I was thinking about the quantum mechanics. No, there was a place in Santa Rosa that closed.
Okay, next time podcast. Oh, what do you like?
Sometimes it
Not
doesn't
news,
work.
so lately. Like, I can't even watch the news on TV anymore. I'm like,
Yeah.
I think it's denial.
Did you? Yeah. I didn't know that. Did you do squeeze?
Yeah. Right, right. So that's the kind of stuff I think I'm always driving to different places. Yeah. You know?
Yeah, I want to do it as long as my body says. It's okay so far.
There used to be, so this is the action.
I never pushed it.
Like you on my Facebook, but that's, this was a really interesting show all about the beginnings of country. It's a series.
Yeah, there's, for the kids.
Yes.
Yeah, I know what you're talking about. I'm sorry? Nord Stream. Not Nord.
So you can,
We know.
Yes. No, they're still around. So they do the thing with the dress codes for the kids. They have to get dressed, girls and gloves, and the guys that are all that. Norquist. Yes, they're still here.
some of them want to have like a skate one, just
So I remember, I'm sure.
and then when you did it,
Oh, no, it goes through my car. Yeah.
and then you're right.
This is Barbara. She was at the school when SPARQ, this is my friend. And she just like the thousand sign, okay. Barbara used to dance. I didn't. I tried taking tango lessons, but I couldn't stop laughing.
My favorite story of Marilyn Smith, she would
Bison, yeah.
Thanks for
like if you heard the little crinkle.
Just about
I'm gonna dog house.
embarrassment. But it was fun.
Your dog?
Well, I think it's a little sick too. I think that I'm not feeling. You got sick.
I feel better this week, but I've been sick for a long time. Don't tell the universe. Let them live in your bubble. Do you hang around kids?
That was always my favorite.
I hang around at home by myself.
Not now.
Good.
The only time, like this is unusual for me. The only, other than this, but the only time I see people is my cousins.
This is so exciting. I'm sorry, but I love seeing the dirty side. Yeah, there's no.
It's like,
Yeah, they have some constraints.
Oh.
And characters.
so I'm,
Well, you should come out at the end of the semester when all the kids have their problems.
great, that'd be cool.
Yeah. So they do, depending on what level they're doing, they'll give a talk in, which isn't a
California.
but they give a talk in here to a panel of college professors.
Wow. Good for them.
Yeah.
You know, I think it's so cool. They have this in high school. I love
This is one of the few high schools in the country that has that.
It has been.
I love that. The picture was like,
Oh.
oh my God. You know?
Yesenia,
Yesenia, sorry.
He's actually like working tonight, whatever.
No, it was like, you're like, and that's the one from home.
Yes.
And that's hers.
There wasn't that much
Wow.
difference. Yeah. She also taught. She
Yeah.
was having this.
Yeah, they use it all the time. They use it everything's open. Yeah, there'll be a schedule out there. They do IMAX movies. Bye, Barbara. Good seeing you again.
Good to see you.
I didn't realize you were here, Shannon.
I was right behind you.
You were right behind me.
She ducked in at the end
I
of
didn't
this
see you.
intro.
Are you recovered?
I just started back down again. I got antibiotics. So big thing is turning back to Yay.
I have something too that won't go away. I don't know what it is, but I think it's gone.
Are you sleeping? That's the thing. I'm not, I don't sleep.
Oh, that's no good.
Maybe I'm super lucky. 4 hours a night, not consecutive.
Do you just keep
whatsoever.
getting that coffee?
Yeah, if I can get 1.5 hours in a row, that's amazing.
It's the coughing that is.
And you try sleeping sleep? In every freaking direction, yeah. And like, I took everything.
Have they given you cough syrup with codeine?
Yes.
And that's the only thing that works for me, but after a week it ran out and they wouldn't give me more. I'm like, right, now I have to sleep again.
Jesus, why not?
Well, they're afraid to get addicted to it. I'm like, I'm not going to get addicted to it.
Trazodone. Do you know trazodone?
Oh, yeah.
Trazodone is not habit forming. Yeah, I think it's.
Is that what's in Needlesaw? Because my sister was so
Trazodone has been around for a really long time.
Don't take some.
Um,
No, the trafficking. So it's
Yeah.
like,
I just
the
over the
name.
counter.
No, it's a prescription.
But it's much better than other things like Ativan and Ambien and those things that you don't really want to take too much.
It just wants to go.
Yeah,
So it's just like, look, I can talk to you in it right now.
Mhm.
I go have a coffee. But at night, it's just.
And, you know,
Yay, Elvis!
but do talk to your doctor about some sleep meds. I think you gotta get to sleep.
Yeah, I take too much sleep.
I've got a big hammer on you.
Mine just work.
Chloroform.
So he was diagnosed as RSV, what you thought?
Well, that's what I thought, because I thought that's what's left, because it's not flu A, flu B, or COVID, right? And then he goes, no, there's actually a lot more out there. So it's not necessarily RSV either. It's, but the last time I had RSV, it was just like this. I couldn't sleep.
Mm.
Yeah.
Yeah, there's a lot of stuff out there. The last 2 times I went dancing, I did something. Oh, no.
But the good news is he's like so highly doubtful that I was contagious. I was like, don't you want to put a mask on before you like look at my nose and look at my mouth? It's like, it's been so long, really.
Yeah, this is what they told me too. I had strep throat 2 weeks ago. That was right before Jasmine's dance.
Oh no.
feel like shit.
Okay, as long as I'm not gonna get my friends sick, that's all I need to know.
You seem fine at the party.
I was okay.
Yeah, you did.
I had cough drops in my mouth a lot during the party, so I couldn't cough, because I didn't want to cough on anybody.
Mhm.
But I made it through pretty good.
Is your tongue just like awful now?
Oh, yeah. Like raw, you sucking in cough drops so much.
Want to have some snacks?
Yeah. Or at least some water.
I need water.
Yeah, they have water, they have water. And cookies. Where'd they go? They went out here.
Out the door
They
to
went
the
into
right, you
classroom,
said.
right? Yeah, they went to the classroom.
So were